In Chapter 10, we're getting into three-dimensional shapes. We're going to combine some of the first couple of sections of Chapter 10. Some of the things we're not going to get into quite as much in here this year, but I wanted to first look at a couple of vocabulary terms. The first is a vertex. So a vertex is just the point where you have some sides coming together. The corner points, so there are multiple vertices, that's the plural of vertex, within the shape. An edge is a line, so where two of the sides come together. And then a face is what's known as like one of the sides of the shape. So a face is just a plane, it is a flat surface. So when you're naming a vertex of the shape, you're going to be naming it like you would a point. So with something like a capital letter A. An edge is going to be named like you would name a line. So something like line segment AB. A face is a plane, so you're going to be calling it something like plane ABC. Something along those lines. A prism has two bases. So all of these are various types of prisms, and it is named according to the shape of the base. So a triangular prism has two triangles, and then connected with rectangles otherwise. A rectangular prism, the bases are rectangles. Cube would be squares. Then you can get into things like pentagonal prism, hexagonal prism, octagonal prism, named according to the shape of the base. A pyramid only has one base. So you can see these are various types of pyramids. We're not going to get too much into where there are various like hexagonal-based pyramids and so on. We'll work primarily with square-based pyramids or occasionally triangular-based pyramids. But these only have one base. The cylinder is kind of like a prism in that it has two bases. Both circles there. The cone is more similar to the pyramid as it only has one base. If you're looking at what's called the net of the shape, the net would be if you unfolded the shape, what things would look like when it was all unfolded. So here, in this first one, we have a circle base, and there's only one base there, so this is going to be a cone. To the right, we have two pentagons, so two bases makes it a prism, and the shape of those bases are pentagons, so this would be a pentagonal prism. Then looking down below, now we're back to circles as the bases. We have two of those, so that is going to be a cylinder. And then this last one, we have a triangle in the center with three sides coming to it, so we have one base. It is a triangular base, so one base would make it a pyramid, so this makes it a triangular pyramid. Okay, so look for the number of bases and then the shape of the base to determine what type of 3D figure it is. A cross section is just if you were to cut the three-dimensional shape here, as you can see, like if I were to cut through there, the resulting shape in this first one would be a square or rectangle of some sort. Here, the cross section, if I'm going kind of horizontally there like it is, the shape that is created would be a triangle. If I were to go the other way and go vertically, cut down through, my resulting shape would be a rectangle instead of a triangle. So you're kind of looking for what's parallel to that, what's mirroring that. Is it mirroring the base or mirroring a side? And that'll be the resulting shape known as the cross section. We also talk about diagonals within some of these shapes. So here I have a rectangular prism. I am trying to find the diagonal, the length of the diagonal here. The diagonal in a three-dimensional shape, we're now looking at going from one corner clear to the other, kind of in the middle of the space here. In order to find that distance, there are two ways I can do this. I can just create, because these are rectangles, I can create some right triangles here. It's a little bit skewed because of it being drawn as a three-dimensional shape, but that is a right triangle on the base of that. So I could use that to find this hypotenuse here, and then this hypotenuse becomes the base of this other triangle, this other right triangle here. So I could do my Pythagorean theorem, so a squared plus b squared equals c squared, and I would do 5 squared plus 3 squared equals c squared. 25 plus 9, that's going to give me 34 for c squared, which means that the square root of 34 is what c is going to equal. So my c here is going to be the square root of 34. That is now one of the legs of this right triangle here. So now I do the Pythagorean theorem again with the 4 and the square root of 34. So I'm going to do 4 squared plus the square root of 34 squared. That will equal my diagonal distance squared. So 4 squared is 16. The square root of 34, when I square that, those basically just cancel each other out, and it leaves me with 34. So I have 16 plus 34, which would be 50 for d squared. So I take the square root of 50, which is going to be 5 times the square root of 2 for d. So this would be my diagonal distance. So we did the Pythagorean theorem twice to end up there. There's a formula that we can use based on this to find it as well. So if you can remember this formula to get the diagonal, all you need are the 3 dimensions of the rectangular prism. So we have 4, 5, and 3 as our length, width, and height, in whichever order you want to do that. So if I do that here, so this is the same shape we were just using. So I have my, we'll say the length is 5 squared, width is 3 squared, and the height is 4 squared. It really doesn't matter which order you put these in. You can add in any order, so this is not going to change anything here. 5 squared is 25, plus 9, plus 16 is going to give us 50, so we end up with the square root of 50. We end up right back where we did before. Square root of 50 is 5 times the square root of 2. So we ended up with the same answer, just kind of a little shortcut here by using that formula. That formula is based on the fact that you're really just doing the Pythagorean theorem twice here to get to that diagonal distance of the rectangular prism. One more thing I just want to touch on very briefly here, and that's graphing in 3 dimensions. We're really not going to get into this very much, but I just wanted to show you what this looks like. So we've been graphing in the coordinate plane where we have the x-axis and the y-axis. And so if I were to graph the point 3, 4, I would go to the right 3, and then I would go up 1, 2, 3, 4. So that would be the point 3, 4. When you get into 3 dimensions, things get switched around a little bit. So we've kind of laid that xy plane down, and the z plane becomes your vertical plane. We're kind of going up into space now. And so the x-axis is the one that's kind of going front to back. Y becomes the one that's going across. And then the z-axis is the one that goes up into that spatial area vertically here. So this is what the point 3, 4, and then 5 kind of brings it up into the air in 3 dimensions. Like I said, we're really not going to get into that, but I just wanted to show you that that is something that you can graph points in 3 dimensions. It just looks a little bit different. Things get oriented just a little bit differently there. So, quick recap here. Remember, if you are looking at the cross section, look where the cross section is being cut and what is parallel to that. That will tell you what the shape is going to look like when you cut that out of there. If you are looking at the net, count how many bases. If it's 2 bases, it'll be a prism or a cylinder. If it's 1 base, it's going to be a pyramid or a cone with those. And then with those pyramids and prisms, they're just named according to the shape of the base.